The study of how we find frequent item sets was one of the earliest directions taken by data mining researchers, and the a priori algorithm is probably the most cited work in the data mining field. The motivation for this study was to determine unusual sets of items that people purchase together in supermarkets. No discussion of finding frequent item sets would be complete without mentioning the possibly apocryphal story of beer and diapers, and we'll tell that one soon enough. But in a rough outline, we're going to start with a model of data called the market basket model, where data consists of sets of items, and sets are called baskets for a reason we'll discuss. And a set of items is called frequent if it appears in some large number of baskets. We'll talk about association rules, which are statements that when a certain set of items are found in a basket, then it is unusually likely that another item will also be found there. And finally, we'll give the a priori algorithm for finding frequent item sets. This algorithm, while it has been improved upon over the years, is the fundamental starting point for all of these improvements. The market basket model is essentially a representation for a many-many relationship between two concepts, which we call items and baskets. On one hand, there's a large set of items. An example is all the different items Walmart sells, of which there are hundreds or thousands. This was the original purpose of the model, analyzing the things people bought at a store. However, the model has many other applications, a few of which we'll talk about shortly. And then on the other hand, there's a large set of baskets. Each basket contains a small set of items. The original picture was that a market basket was a shopping cart, a physical, that is not electronic, and customers would wheel their market basket up to the checkout. The cash register would group all the items in the basket together in one bill, and that bill would be stored in the store's computer system. Thus, by mining the contents of the various market baskets, the store could learn what people bought together, a hamburger and ketchup, for example. That, in turn, would let the store figure out some ploys to increase sales. Think about what a store might do to exploit this information. We're going to return to the subject shortly. The most useful and also most basic question to ask about data in the form of market baskets is to find those sets of items that appear in some minimum number of baskets. We'll define the support for an item set to be the number of baskets of which that item set is a subset. We can give the support either as an absolute number or as a percentage of all the baskets. Data mining problem called frequent item sets involves a number or percentage S called the support threshold. Any set of items with support at least S is called a frequent item set. Okay, here's a very simple example of data in the market basket model. Okay, there are 5 items: milk, Coke, Pepsi, beer, and juice. The support threshold will be 3. It's an absolute number, not a percentage of the baskets. Here are the baskets. We're using M for milk, C for Coke, and you can probably figure out the rest. Okay, now, what are the frequent item sets? Well, almost all the singletons are frequent. Each of the items except Pepsi appears in at least 3 baskets. For example, beer appears in B1, B3, B5, B7, B6, and B8. Okay. Pepsi itself is not frequent because it appears only in B2 and B5. There are also some frequent doubletons. For example, milk and beer appear together in the 4 baskets shown. Okay. And beer and Coke also appear in 4 baskets. And finally, Coke and juice appear together in 3 baskets. But no other doubletons are frequent. For example, milk and juice appear together in B2 and B6, but in no other baskets. Okay. Also, there are no sets of 3 or more items that are frequent, so we're done. We have found all the frequent item sets. One might have included the empty set, that is surely a subset of all 8 baskets, but the fact is uninteresting and we usually ignore the empty set. As I mentioned, the original application for this sort of analysis was looking at the things people bought together in a store. In this case, the items really are the items one might buy, and the baskets are sets of items bought together by one purchaser. Okay, there's a story that the first interesting discovery of a frequent item set was that diapers and beer were frequently bought together. Now, once you think about it, it makes sense. If you're buying diapers, you probably have a baby at home. If you have a baby at home, you probably aren't going out to a bar to drink, so you bring the beer home. I have heard several people claim that they themselves discovered this, so I suspect that really nobody did, and it's just an illustration of something that you wouldn't think of without a way to analyze massive amounts of data, but which proves to be true and explainable rationally once you see it. The first thing marketers did with information like this was to reorganize their shelves. They would put the diapers and beer near each other, but put another item that made sense between them, like potato chips. But there is a more subtle way to exploit the data mining discovery. Suppose we run a sale on diapers, but we raise the price of beer. People will come in to buy the cheap diapers, and while they're there in the store, they're likely to pick up some beer, not noticing the price is too high, or even if they do, figuring it doesn't make sense to drive to another store just to buy beer. Everybody wins. The customer doesn't lose money, and the store gets more customers and, on average, receives the same amount from each customer. Only the competitors of the store, who don't have their own data mining experts, lose. Incidentally, a subtle point here is that there is causality operating, and it's very hard to deduce causality from data. That is, if you don't think about the causes underlying the data, you might imagine that you could just as well run a sale on beer and raise the price of diapers. But people who come in for the sale on beer are not going to buy diapers if they don't have a baby. I just want to point out that these techniques are appropriate mainly for brick-and-mortar stores. A brick-and-mortar store needs to know that lots of people buy diapers and beer, or else they're wasting time and money optimizing the sale of something that is rarely bought anyway. That viewpoint matches well with the idea that we're looking for high frequency rather than correlation between rarely purchased sets of items. Online stores, on the other hand, do not need to rely on high frequency since they can tailor their store differently for each customer. Thus, entirely different forms of analysis are needed for online stores, and we'll cover that as a separate topic. Here's another problem that uses the same data model with an entirely different interpretation. Suppose our data is a collection of documents. Think of the sentences that appear in one or more documents as a basket. The items are the documents themselves, and the basket corresponding to a sentence contains all the documents in which that sentence appears. Now, what does it mean if a set of items appears together in many baskets? The item set is a set of documents, and these documents, or items, appear in a lot of baskets together. That means there's a collection of documents in which a lot of the same sentences appear. Documents that look like that may well be an instance of plagiarism. It is interesting to note that in this case, the items, the documents, are not in the baskets, which are sentences, and in fact, it's the other way around. But as we mentioned, items and baskets form a many-to-many relationship, and you can always view such a relationship from either side. However, when it comes to the algorithms we'll discuss, there is an asymmetry. We assume that baskets contain small numbers of items, while items can be in a very large number of baskets. The algorithms would take too much time if baskets contain large numbers of items, because the work done processing each basket is normally quadratic in the number of items it contains. Here's another application involving documents. Let the baskets now be the documents, and let the items be words. We can think of a basket, a document that is, as the set of words it contains. But remember what we just said. We have to be careful that the average basket doesn't contain too many items. If documents are books, for example, they would contain thousands of different words. But if documents are tweets or emails, we're okay, because these are typically short. In the case of tweets, they're necessarily short. We can cut down on the number of words in a document by ignoring stop words as well. These are the common little words that usually don't carry any significant meaning. Now, what does it mean if a set of items is frequent? That means we have a set of words that appear together in a large number of documents. By the way, that's another reason to get rid of all the words that are not pretty rare, or we'll just discover that words like the and appear together in many documents. That's a big deal, right? On the other hand, if rare words are relatively frequently found in the same documents, then there might be some connection between the words. I'm supposing, say, that Brad and Angelina might be two such words. Or is that old news? Probably is. Anyway, just to remind you of the scale of the sort of problem we're thinking about, if we're dealing with real market baskets, a big store like Walmart will sell 100,000 different items, and it stores billions of baskets in its database for analysis. On the other hand, the web has billions of different words, most of them, by the way, are misspellings, and many billions of pages. Often the problem of finding frequent item sets is characterized as the problem of discovering association rules. These are rules that say, if a basket contains some collection of items, then it is also likely to contain another particular item. The notation for association rules that we use is shown here. Informally, if we assert an association rule that says I1 through Ik implies J, we mean that if a basket contains all of I1 through Ik, then it is likely to contain J as well. The degree to which this event is likely is called the confidence of the rule. It's the fraction of the baskets containing I1 through Ik that also contain J. For example, here are the 8 baskets we saw earlier. A possible association rule is this: milk and beer imply Coke. Let's focus on the 4 baskets that have both milk and beer. We see that B1 and B6 do have Coke, while B3 and B5 do not. Thus, 2 out of the 4 baskets with milk and beer do have Coke, and the confidence of this rule is 50%. One reasonable thing to do with market basket data is to find all association rules that have a minimum support S and a minimum confidence C for some values of S and C that you decide on before you run the algorithm. The support of an association rule is the support of the side to the left of the arrow. That is, it is the number of baskets containing all the items on the left. The hard part of finding association rules is really finding the frequent item sets. If an association rule like this has support S, then the set on the left will be frequent with support S, that is the set I1 through Ik. But if the confidence of the rule is also high, that is, the confidence C is close to 1, then the set of items with J, the item on the right thrown in, will have support CS. Now, if C is large, then CS will be close to S, say perhaps 1/2 of S. Okay, and here's a recipe for finding all the association rules with support S and confidence C. Start by finding all the item sets with support at least CS. Also find the item sets with support at least S. That will be a subset of the first set of item sets. Let's focus on an item set in the first collection, that is one with support at least CS. Suppose it has k plus 1 items as members. There are k plus 1 subsets of size k, each formed by removing one of the items. I've abused the notation a bit by singling out one of them as j, the item to be removed, leaving I1 through ik. But in fact, we have to do this k plus 1 times 1 for each of the items. Having removed j, look at the support of the remaining set I1 through ik. If it is at least S, we might have an association rule with the set on that set on the left and the k plus first item j on the right. Now, suppose the set without j has support S1, and with j the support goes down to S2. Then the confidence of the rule is the ratio S2 over S1, because that is the fraction of the baskets with I1 through ik that also contain j. If that confidence is at least C, then we have an acceptable association rule. We're going to look at finding frequent item sets in a setting where the basket data is kept in a flat file, not any sort of a database system. As I tried to argue on the previous slides, it is finding frequent item sets that is the hard part of finding association rules. So even if our goal is to get association rules, and in many cases we really want only the frequent item sets anyway, not the association rules, we're going to talk from this point only about the problem of identifying the frequent item sets. We assume the data is so big that it has to be stored on disk. Since reading data from disk often takes more time than what you do with the data once it is in main memory, our primary goal will be to minimize the number of times each disk block has to be read into main memory. We're also going to assume that data is stored basket by basket rather than by item or in any stranger way. And we're going to have to find for each basket all its subsets of a particular size. We can do that in main memory once the basket itself is there. We can use k-nested loops to generate all subsets of size k. Since we assume baskets are small, and often k will be only 1 or 2 anyway, we're not going to worry about the cost of doing this generation. However, you should be alert to the possibility that if you were asked to generate all subsets of size 100,000 from a basket with 1,000,000 items, you just couldn't do it. Okay. So here's a picture of what we imagine the file looks like. Items have been coded as integers, so the file is a sequence of integers. We need to wait to indicate where one basket ends and the next begins, so we might use an integer like -1, which we suppose can't represent an item, as the separator for baskets. As we mentioned, we can focus on the number of times a disk block is moved between disk and main memory. Turns out that the algorithms we will study each operate in passes. During a pass, the entire file is read block by block in order. A surrogate for the cost of the algorithm is thus the number of passes. The number of disk IOs is that number of passes, times the number of blocks that the file of the basket occupies. Another non-obvious point is that for the algorithms we consider, the limiting factor is usually how much main memory is available. So for example, it is common to have a pass where the file of baskets is read, and as we read the baskets, we count all the pairs of items contained within that basket. We need to have a place in main memory to count each pair. So that means at least a few bytes per pair. If we have 100,000 items, then there are 5 billion pairs. At 4 bytes per count, that's 20 gigs of main memory. Okay, we can do that, buy a little extra for our machine, or use several processors. But if we have 1,000,000 items, that's 500 billion pairs, and we can't really manage all the counts in main memory. And if it isn't obvious, using disks to store the counts will not work. The counts we have to increment are essentially random, so if even half the counts need to be on disk at any time, we have a 50% chance of needing 2 disk IOs with every increment. I'm going to concentrate on how you find frequent pairs of items. Often finding frequent items, that is, sets of size 1 or singletons, is not too hard because there aren't so many items that we can't count them all in main memory as we make a pass through the baskets. But it's also common for the number of pairs to be too large to count them all in main memory. You might think that there are even more triples of items than there are pairs. You'd be right. However, the algorithms we'll cover exploit the fact that once you have the frequent pairs, you can eliminate most of the triples and not count them at all. One might ask why there shouldn't be lots and lots of frequent triples. The reason is that if we're going to bother to do a frequent item sets analysis, we don't want so many answers that we can't even think about them all. As a result, it is normal to set the support threshold high enough that it is hard for a large item set to be sufficiently frequent. As a result, most of the sets that will meet the thresholds will be singletons or doubletons. The bottom line is that we're going to concentrate on algorithms for finding pairs. The extension to larger item sets will be given once and can be used with any of the algorithms we discuss. Let's start by talking about what we might call the naive algorithm. We want to read the baskets in some number of passes, so why not use just one pass and count all the pairs in main memory? We mentioned this briefly, but just to make sure we understand what happens when we process a basket, we use a double loop to generate all the pairs of items in the basket, and for each pair we add 1 to its count. This algorithm actually works, provided there is enough space in main memory to count all the pairs of items. The number of bytes we need is roughly the square of the number of items in our data. That is, the number of pairs of items is the number of items choose 2, or approximately half the square of the number of items. And if we can count each pair in 2 bytes, which is possible if the threshold is no more than 2 to the 16th, then the number of bytes we need is exactly the square of the number of items. If we need 4-byte integers to count, then we need twice that square. And just to recall, the typical number of items, if you're Walmart, the number of items is about 100,000, so you might be okay. But if you're dealing with items as web pages, then you're definitely not okay. Before we proceed, I need to talk in a little more detail about how you organize main memory to do the counting of pairs. There are actually 2 approaches, and which is better depends on whether it is likely or unlikely that 2 given items ever appear together in a basket. One approach is to maintain a triangular matrix. I'll talk about this on the next slide, but the idea is to maintain a 2-dimensional array where A of I and J is only there if I is strictly less than J. The second approach is to keep records with 3 components, I, J, and C, meaning that the count for the set of items I and J is currently C. You organize this collection of records by indexing on I and J, so given a pair IJ, you can quickly find its record and increment its count, or just read its count if that's what you want. The triangular matrix approach requires 4 bytes per pair of items. I'm going to assume from here on that integers require 4 bytes, even though, if as we just mentioned, it is okay to keep them small, then fewer bytes could be okay. It is even possible in some circumstances that you need more than 4 bytes, but I'm not going to worry about that case either. On the other hand, if we keep a table of triples, then we need 12 bytes per pair, 4 each for I, J, and C. But the advantage is that a pair only needs a record if it appears in at least one basket. As a result, the space requirement for the tabular approach is 12 bytes per existing pair, but not per possible pair. Here's a picture of the difference. For the triangular matrix, you need 4 bytes per unit area of the triangle. For the tabular method, you need 12 bytes times the fraction of the area that represents pairs actually present. So if more than 1/3 of possible pairs are present in at least one basket, you prefer the triangular matrix. If you expect fewer than 1/3 of the possible pairs to be present in the data, then you should go for the tabular approach. Now let's look at how we construct a triangular matrix given that this structure is not exactly built into most programming languages. First of all, we'll assume the items are represented by consecutive integers starting at 1. If items in your data are represented by their names or by integers that are not consecutive, then you need to build a table to translate from an item's name in the data to its integer. A hash table whose key is the original name of the item in the data will do this just fine. Okay. We're counting sets of 2 items, so we can think of each set as an ordered list of length 2. That is, we'll count all I and j such that I is less than j. I want to use an order for the pairs that look like this. Okay. If there are n items in total, then first come the n-1 pairs whose smaller member is 1. These. These pairs are in order of their larger member. Then come the n-2 pairs whose smaller member is 2. Again, these are ordered by the larger member. Then the n-3 pairs with 3 as the smaller, and so on. What we really have is a one-dimensional array, and we need a function that takes I and j, where I is less than j, and turns it into the position in the array belonging to this pair. Here's the magic formula. I'll let you figure out why it works, but for example, if n equals 10, let's look at the pair 3, 5. I claim it is at position 2, that's I minus 1, I is 3 of course, times 10, that's n, minus I over 2, that's 3 halves, plus 5, that's j, remember j is 5, and then minus 3, which is I. You work that out, it's 19. Okay, that makes sense because there are 9 pairs ahead of the pair 3, 5 that have a 1 as the lowest member of the pair. There are another 8 pairs that have 2 as the lowest, and then there's one more pair, 3, 4, that comes ahead of 3, 5. The total number of pairs that are represented is n choose 2, or about n squared over 2. And we use 4 bytes per pair, so the number of bytes needed is about 2n squared. If we use a table of existing pairs, then we need space 12p for the triples, where p is the number of pairs that occur in the data. As we mentioned, this amount of space is less than that of the triangular matrix as long as p is at most 1/3 of the possible pairs, or about p less than n squared over 6. However, for this method, we also need an index of the pairs of integers so that we can quickly find the record for that pair. This structure also requires space depending on how we implement it. For example, we might implement a hash table, in which case we need pointers to link a list for each bucket. So let's say here's the hash table, here's a pointer to the first element, so we'll have an I, a J, and a C, and then a pointer to the next element, and so on. That would add another 4 bytes per pair. In particular, not counted in the 12p is all the space for the bucket headers. That's probably not too much. But then another integer at least for each of the links. That is going to lead to a cost of about 16p rather than the 12p. And in addition, again, there's the cost for the bucket headers, which is probably negligible.